Okay, everybody, so part A, how can this linear equation be written as a dot product? Well, every linear equation, so you see that there's no z squareds, there's no x times y, there's nothing quadratic or degree 2 about it, or higher. And so what we do is we just pull off these coefficients, and they become a vector. So I'll just write that in words. Coefficients become a vector. And then also the variables, the x, y, z, they become a vector. And then dot them and equate, so make an equation, equate it to the constant. So this constant term, it doesn't have a variable, so we call it the constant term. And so this will work every time. This process works for every linear equation. Here's an equation, and we can write it as a dot product equation. Okay, so let's use formulas. So I'm just going to take 2 minus 3, by the way, minus 5, because this plus 5 will come over to this side. But you'll see that in a moment. Dot x, y, z. Well, if I just did this, then I would get 2x minus 3y minus 5z. 2x minus 3y minus 5z. And so now you see that we're getting the correct minus 5. But we want that to now be equal to, so we're going to put this equal to minus 2, because that's what's over left on the right-hand side. So this, I like to put an exclamation part when I'm reminding myself, like, I'm forcing this to be equal to negative 2. Like, this expression doesn't need to be equal to negative 2. Only for very special x, y's, and z's will it be equal to. So anyway, this is equivalent, so here's my little symbol for equivalent, to the formula 2x minus 3y equals 5z minus 2. So these two things are the same. And I'll hold off on a picture until part B, which will be full of pictures. But, okay, no, I'm not going to hold off. So somewhere is 2, negative 3, negative 5. It doesn't, this is just my cartoon, so I'm just going to draw this vector. Here's 0. And so if this is 0, let's say we're in we are in three-dimensional space, then 0 is one of the entire plane of solutions that solve this vector equals 0. But then we want it to be equal to 5, so actually we're going to shift forward that plane to somewhere sort of off the origin, but with the same direction, or with the same normal vector right here. Anyway, this is just a picture that I'm not going to explain, because part B is all about explaining it. So part B. For a fixed vector n, by the way, when I write n in n to the r to the n, that's a little confusing, because here this n is meant to be like 2, 3, 4, 5, a number. This is a number, like an integer. And this n is supposed to be a vector, so like n1, n2, and 3 would be an element of r to the 3. So, often in math, people just write things down, hoping that you understand what they mean. And you're never going to escape this, because, because nobody's perfect, right? They write things like this. Anyway, okay, and variables x in Rn, explain how the solutions to n dot x equals 0 are different than solutions to n dot x equals 5, which are different than solutions to n hat dot x equals 5. This we say is n hat. That means it's a unit vector. It's, n hat is equal to the vector n divided by the vector's length, so that now the length of n hat will be actually 1, and you can check that. It's a previous problem. Okay, so what am I going to do? So first, let's just make a calculation. See that, okay, these are words, but see that if x equals the 0 vector, then what do I have? N dot x equals n dot 0 equals 0, a real number. Okay, so now I guess these are all words. You, of course, don't have to color code your answers, but I'm color coding them to see how the words string it together. And so, so now in words, I'll say what this means. Plugging in x equal to the 0 vector, right there, that's the 0 vector, and here's the 0 number. These are two completely different zeros, right? This 0 vector is really 0, 0, 0, some amount. And this 0 number is just 0, the number. Okay, so I got sidetracked yet again. Let me finish this sentence. See that if this, then this. So solutions to n dot x equals 0 always include, this is the key, always include the origin. The origin is our special name for the 0 vector. The origin. Okay. What does that mean in a picture? It means that if we have some vector n, then it starts at the origin, and it goes out to some vector n1, n2, 3, right there, maybe that point. And then right here, at 90 degrees, is an entire plane, all solutions to n dot x equals 0. They must include 0. So the plane, this plane goes through origin. The solution plane goes through the origin. Okay, that's what it means. Let's make another calculation about n dot x equals 5. For n, well, I'll write it the other way, n dot x equals 5, the solutions never include the origin. This is the main insight, because if you plug in, so if you plug in x equals the 0 vector, then what do you get? You get n dot 0 equals 0. But 0 is not 5. We wanted n dot x equals 5, so n dot 0 does not work. Okay, so this means, what does this mean? It means solutions, solution plane does not pass through 0. So let's draw a picture of that. Maybe we'll draw a two-dimensional picture. Here's my two-dimensional space. Maybe here's n. And the solution plane then would be something like this. This is all solutions to n dot x equals 5. And notice it does not include 0, 0. This line does not go through the origin. Okay, in comparison, we might choose a different color. Now this is solutions to n dot x equals 0. It passes through the origin. It includes that point. That's the difference. So all these, linear equations are going to give flat solutions, things, depending on the dimension, but they're always flat. And the key observation is whether or not 0 is a solution. Okay, because if 0 is a solution, we have one way to find an easy solution, and you'll see in linear algebra that we can use that fact to solve many other things. Okay, but for now, you just need to show, like, okay, when does it have the origin? Here it does not have the origin. And finally, the last one, n hat dot x. Let's look at n hat dot x. N hat is a unit vector. That means it has length 1. Now, if the question asks us to consider the equation n hat dot x equals 5, and here's the key. Its solution plane, and plane here is just a word for any flat object. Its solution plane, well, it won't pass through the origin because we're shifted off by 5. But the key is will be exactly 5 units away from the origin, Since, and now we calculate, so we'll calculate with formulas. If x is equal to 5 times n hat, well, that would be, here's one n hat, here's 2 n hats, here's 3 n hats, 4 n hats, 5 n hats. That will be a length of 5 units. And the claim is that this point is a solution. So let's calculate. N hat dot x equals 5. Is that true? Well, n hat dot 5 n hat equals, and now we can pull the 5 out. This is by linearity. The dot product is linear. So the 5 can pull out, and it leaves n hat dot n hat. But that's 5 times 1, because n hat is a unit vector. And that is 5. Perfect. So the answer here is yes. Okay, and so here's solutions to n hat dot x equals 5. And so we've observed that the solution plane, at its closest point, of course, this point is much farther away than 5 units. This point, over here is also a solution, and it's more than 5 units away. But at the closest point on that plane, it will be 5 units away. 5 units away because we calculated that 5 n hat solves the equation. Okay, so good. I have pictures, I have words, I have formulas. And, I was quizzing myself. So that I also solved it earlier, sort of in a different way. So you can maybe compare these two solutions. Here's part A of my other solution. Here's part B. Linear equations give flat geometry in words, and in pictures here are the flat things. And here's, the origin. It does not have the origin, and it's 5 units away. And those are the main differences between this equation, and this equation. Includes the origin as a solution, is shifted off the origin. All solutions are shifted off. And here they're shifted by exactly 5 units because we used a unit vector.